So, yes, the best session right after lunch where everybody is calm. So, I should say this was a working title. We had a more snappier one in mind, but never got around to actually do that. So, apologize for the very long title, which is almost an abstract in itself. So, this is joint work with Martin Nelsman, and I'm just here to present. Well, I also did some work. So, why are we doing this? So, we're doing this in the context of a parallel functional programming language, and we're not talking about concurrency. We are talking about data parallelism. And one of the problems, sort of, and a still open research problem, is how do we deal with irregular nested parallelism. So if we have, let's just say that we have a map of maps, and these inner maps, they have different size, then we need to do something in order to balance the work. Guy Breller did some really nice work on making a flattening transformation. So we have this irregular nested one, and we can always transform it into a flat parallelism. Unfortunately, that can have some significant overhead. So how do we deal with that? How can we avoid using this sort of transformation, which might have some overhead? It turns out that functional programming is really good for describing parallel computations, and in particular, sort of our old friends like map and fold, also known as reduce, and even scan. They're really great for saying, I have this large collection, also known as a nested array or something. I have a lot of data, and I want to map this function over it, or I want to reduce it to make it smaller, or filter it, or what have you. What is sort of the stable functions that we see everywhere is good for sort of keeping the data constant. They're not that natural if you sort of have a problem with a few parameters, and then you sort of unfold it or you expand it to a large one. So in Futhark, which I will come back to, and I will give you an explanation of what Futhark is and show you a few programs, since this work is in context of Futhark. We also have a function called expand, which is exactly for capturing sort of these certain classes of irregular nested parallelism. So we have, let me just show you expand. So here's the type of expand shown with sort of all the sort of small bells and whistles. So if we just read it as an OCaml type, we can see that it's something polymorphic. So it's a function that takes a polymorphic thing and then gives us an integer. And then we have another function we take as argument that takes a thing and an integer, and then it gives us a b. And then it transforms an array of a's into an array of b's. So that's just the type. What this function is doing is that these two functions are basically sort of how we are expanding it. So first, we need to know sort of the size of the resulting array. So how many elements we have in the result, so how many b's will we have, and then a function taking not only an a but also sort of an index, I'd say, that we can compute that we can use to compute the b's. So this is a function that will expand each a into to potentially large number of b's. And if we just want to think of what is the semantics, this is not how it's implemented. This is sort of the semantics. So it's not that we can express something new with expand. It's just that we have a pattern that can be implemented in an efficient manner. And I should say that here there's sort of iota. This is just a function that generates an array with that number of arguments, and that's an array of integers starting from 0 and up to 1 less than the argument. And flatten, that's also known as concat, so that's something that sort of in Haskell it would take a list of lists and return one list. However, in Futhark, flatten or not, all the arrays should have the same size, all the inner arrays. So that's a limitation that beginners often run into. So this is where the irregularity is disallowed. So this is why this is not the implementation, but sort of you might think of it as semantics if you to just implement expand in Haskell or OCaml or standard ML or what have you. So this is just expand, and expand is important. That's sort of to make easier, because the problem we are dealing with in the paper I'm presenting is it's not so much a new building stone, because we have some great building stones, namely higher order functions. They're really great at capturing patterns even for irregular parallelism, and with expand we can deal with a large class of problems. However, when you sort of start to get into it and you make this sort of sequence of higher order functions, it becomes sort of a big thing. And you have to name a lot of things, because otherwise you cannot keep track of your huge expression, and it's not that ergonomic. And I'm sure that every functional programmer knows what I'm talking about. The younger ones think, well, I'll just turn to point-free notation, and the older of us know that no, down that road by madness. So how can we make it a bit more ergonomic? And sort of one great sort of DSL that a lot of languages have is comprehension. So basically this work is adding list comprehension, or except that it will be array comprehensions, to Futhark. And here is just sort of what I could fit in of the grammar for list comprehensions. It's basically taking Haskell's syntax. So we have sort of lots of the usual expressions. We have numbers and variables, tuples, lets, and higher order function literals, function application, and lots of other stuff. And then we have this new expression where we have an expression, a bar, and then a quantifier. And a quantifier is either a binding or it's another expression that's a guard or a filter. And then we have, you might say, Cartesian product, that's a comma. And then we also have the parallel or SIP comprehensions from Haskell as well. We concentrate mostly on sort of standard ones. And if you have not seen Haskell list comprehensions, here is a sort of a small example, motivating one, which is sort of quite hard to actually write with sort of standard higher order functions. So here we want to find all the Pythagorean triples, that is x, y, and z, where this equation holds. And here we want them all those who are less than 100. And basically we take and sort of as a sort of in order to get them unique, we want x to be smaller than y, otherwise we'll have sort of symmetric solution. So that's, but here we have sort of a list expression. So here's the final result, and we want sort of for all x in the range from 1 to 100 with a step of 1, take y from x to 100, step of 1, and z in the range of y to from up to 100, step of 1, where x plus y plus z is less than or equal to 100, and where x squared plus y squared is equal to z squared. So here it's sort of like, it's deeply, well, it's not deeply, but it's a bit irregular because the range of y depends on x, and the range of z depends on y. So we have this regularity, which makes it hard to do with sort of straight maps at least. I mean, we can do it with straight maps, and then concats, but these concats would have uneven size. So here's how it looks like if you use expand and filter. And it's sort of like, if you read it from the other way around, then here's the last filter, that's the filter here. Here's the other guard, that's the guard here. And these two expands are basically for y and z. And as you might have guessed by the creative naming here, and the weird sort of, why did I translate that? This is not me who wrote that solution. So I'll get back to how can I get a program to, I want to specify this, and then I want to get this because I can't remember how to use expand and so on. So yeah, I'm lazy. I want to automate things. Another example, which I'll also show, just because all good talks should have graphics, just to emphasize that functional program is not just about Greek letters. So here's a graph, but I'll come back to how to do line drawing. Basically 3 slides to show one list comprehensions later on. Well, back to that. First, I promised to say a bit about what is Futhark, and it will be a very short bit. So there will be a lot of slides, but it's basically a programming language targeting highly parallel hardware, such as GPUs. And it's an ML dialect, meaning that when you program in it, it feels a lot like programming in OCaml, standard ML, and Haskell, sort of in the pure, sort of, you might say, the core part. And then it has it has numeric types, integers, floating points, multidimensional arrays, no lists, only arrays. And lists are strict, so it's a strict language actually. And it also have higher order functions and modules which are compiled away. So this is basically a very short introduction, not really introduction, just stating what it is. And it's based a lot on, again, we have higher order functions. They're actually sort of built into the language, and the compiler knows how to fuse and optimize these, map and reduce, and sort of a lot of it is a sort of standard functional programming compiler with standard optimizations, but there's also a few sort of special sauce. So one is that we can actually specify the types and have a lot of things which is hard on GPUs is actually making things polymorphic in the size in order to fit the kernels and tiling them and all sorts of stuff that you don't want to know about. I definitely don't, and I'm happy that the compiler knows. And we can specify that, so we have sort of these numeric numbers in our types, and we are working on making these more general. And these types, these size constraints, they will actually be enforced. So they will, you'll get an error if they don't work. And a lot of the compiler is basically compiling away all these layers of abstractions. And in particular, some abstractions like arrays of tuples, they are represented as tuple of arrays, meaning that tuples are basically unboxed and compiled away, so you can sort of use zip and unzip without worries. They're basically no ops. So getting back to this, 3 slides for one list comprehension. So showing how to take an array of lines and compiling that into an array of points. So basically we have sort of the starting point and the end point of a line, and then we want to sort of calculate all sort of what are all the pixels or the part of the grids that should be colored by some lines. That's the problem. And basically the next slides here, they're just to show you a bit of like what does Futhark look like, and indeed it's not scary. It looks a lot like sort of your standard ML dialect. Sort of we have type declaration where we can say we want a point, and the line is 2 points. And then we have some functions over, this is basically just to compute the slope of a line, which we can then use to sort of find out if I want the ith point on a line, how can I compute that? We also have this for the Bezier curves and other stuff, and it's, I mean, yes, the font is starting to get a bit small and it goes into page numbers, but it's, again, this is pretty much textbook. It is actually taken out of a textbook, functional programming. And then sort of previous works, then the next slide would have this expand function and say, look, now we can actually capture that and get a work efficient version. And you could that if you were an expert Futhark programmer. Then I came along and I said, well, I'm not an expert Futhark programmer, I'm an expert functional programmer. So let me just write this list comprehension instead, and then get the compiler to basically, this will basically compile into just a single expand expression. So this was just, again, showing you that, at least I think that list comprehension fits nicely into Futhark. The interesting part is, how do we then translate comprehensions into to Futhark, and that's for sort of it's not that sort of again, the interesting part here is that we cannot use the standard transformation because that will use usually it will use concat and map, and in particular this concat will be over irregular arrays. Sometimes when I say concat and map, we'll say map concat or concat map, also known as bind, and have a monadic interpretation, but we will have a sort of slightly different translation. So, yeah, here comes the Greek letters, or at least, well, not Greek letters. Oh, there's a lambda. But again, there's this sort of a standard translation function here, coded with much sweat and pain in LaTeX rather than the Haskell version. But basically, when we have a comprehension, we compile that into a map over sort of the list or the array of values that this quantifier generates. So when you see something like that, it's really just a map. And here is sort of a bit meta languages in Roman, and Futhark is in, or at least it should be in monospace. So here's the translation of a quantifier, and the interesting part is, how do we translate of a full comprehension? How do we translate a quantifier? That's a function, a semantic function that takes 2 arguments. Basically, it's 2 accumulating arguments here. We didn't have time to make it elegant. One is sort of in the value part, and the other one is in the pattern part. So remember, this is actually a pattern, so it might deconstruct tuples and bind names and so on. And we translate those sort of just both at the same time. Yeah. So we take accumulating parameters, and then we return a pattern to bind in the map, and not the body, but the expression to map over. And sort of what might be surprising is that the thing that the parallel quantifier, where you basically have a zip that, well, I mean, that basically comes out as a zip, so that's sort of straight up as it used to be. And the Cartesian product is also not that, again, that's not the interesting case. In fact, the one is when you have like this inner bind, where you translate that into, that's where we translate something into an expand. And this weird circle plus here, that's sort of meta level for tuple append, because at the meta level we can append tuple. We cannot do it in the source language. So basically we sort of, if we have a tuple, then we make a pattern for a tuple which is one larger. In the same way in the value, if we have a value, then we can construct a tuple. Well, if it's a tuple, then we will not make nested tuple, but we'll make a bigger tuple. And we're using two meta functions here, size and fetch, and that's basically sort of, that's where the magic happens, you might say. So in some sense, this translation is also a fusing of certain sort of simpler constructs, and the fusing is sort of happening in these two meta functions here, which I have on the next slide. And these are simplified versions, but it's basically that if we have an iota, so we need to know the size of things, so this is the limitation, that if we don't know what we are expanding into, then it doesn't work. So this will sometimes fail at the moment. It's not intended to fail once we get it done and moved into the language, but the prototype, it will sometimes fail. But for certain expressions, we do know what is the size that we need to compile things into. So for iota and maps and range, then we actually know the size of things. And there shouldn't be an F, that's wrong. Similar, when we get a certain element, we can also generate that fairly sort of without too much ceremony. So again, this thing will sort of, by that translation, translate into this nest of higher order functions. So many words. In a few words, we have added list comprehensions to Futhark, and it seems to work really well.